We're going to begin our video lessons on Chapter 9, Chemical Bonding 1. Recall that this week we have two chapters to go through, Bonding 1, Chapter 9, and Bonding 2, Chapter 10. With Chapter 9, we're looking more about the Lewis dot theory and how atoms come together either with an ionic or a covalent bond. And we'll talk about bond dissociation energy, that energy that's needed to break the bonds that form. Of course, in Chapter 10, we start thinking about molecular geometry, a three-dimensional space that the atoms occupy. Let's go ahead and look at our first slide of Chapter 9, talking about those bonding theories. Bonding theories explain how and why atoms attach together to form those molecules, and they help to explain why some combinations of atoms are stable but others are not. Why is water, two H's bonded to an O and not one of each or three of each? Happens to be because of the stable arrangement of that electron cloud. We then use the way that they bond to help predict the shapes of those molecules, and the shapes of the molecules give us so much insight into the chemical and physical properties of those molecules we have. So those chemical physical properties of compounds can be directly determined from the shape of the molecule once we bond the atoms back together. The Lewis bonding theory is really one of the simplest theories to help explain why atoms bond the way they do. Here's a picture of G.N. Lewis. Lewis bonding theory also is discussed with acids and bases as well, so his name appears several different ways throughout our chemistry book. The Lewis theory is often called the electron dot theory as well. He emphasizes the valence electrons to help explain bonding. When we use the Lewis theory, we draw structures that are known as Lewis structures or electron dot structures, and allows us to predict many properties of their molecules and helps explain stability, shape, size, and polarity. When chemical bonds form, they do so because the new bond is at lower energy than the original atom was by itself. Forming bonds lowers the potential energy between the charged particles. A chemical bond forms when the potential energy of the bonded atoms is less than the potential energy of the atoms in their separate forms. So we have so many interacting energies to calculate when you need to consider the following interactions. Nucleus to nucleus. If we think about those positive protons inside the nucleus, and as I bring two atoms near each other, this is actually a repulsive force. Positive charges that are alike repel. We also have these energy levels that contain electrons. These like charges, electron clouds, would also repel. The only really attraction is opposite, and basic laws of electricity say, again, bringing electron clouds near each other are going to cause them to repel. But if I have a positive nucleus and the negative energy level, those opposite charges actually create an attraction. When we start thinking about the way molecules align or even the way that molecular geometry forms, we want to alleviate as many repulsive forces between like charges as possible. We want to bring together opposite charges and align them and alleviate repulsive charges by arranging the molecules where opposite charges are near each other. When we begin to classify types of bonds, we'll talk about three and introduce the three, but really focus on the first two. When a metal bonds to a nonmetal, we call those formula units or ionic compounds, commonly called salts. We talk about an electron transfer. The metals lose and nonmetals gain, forming what we called ions. Ionic bonds are electron transfer. When a nonmetal bonds to a nonmetal, we call those molecules. Those molecular compounds share electrons and form covalent bonds. The sharing of electrons in molecules, the transferring electrons in formula units. Ionic compounds are called formula units, the basic building block of a salt. The third is when a metal connects to a metal and creates this electron sea. Electrons are then pooled together, and we call that a metallic bond. The reason that metals are such great conductors of electricity are these metallic bonds, where atoms of metals just simply pool their electrons to create a stream of electron flow. Visualizing the three different categories of bonds. Ionic compound: when a metal connects to a nonmetal, they form ions. Here we see a picture of a sodium ion and a chloride ion. This forming, of course, ordinary table salt. Water represents a molecular compound. All nonmetals covalently bonding means they're sharing electrons. And in this particular picture, I see a sodium. This is just a hunk of sodium metal. And inside of this structure, we can see in a whole electron cloud, or a sea, or a pool of electrons generated between those sodium atoms, creating a pool of electrons that help conduct electricity. Let's focus on ionic bonds in our next slide. When a metal atom loses electrons, it becomes a cation. When I think of this cation, I said think of this little T as a positive sign. Metals lose electrons and become more positive. Metals have low ionization energy, and this was a term we defined really as the ease of losing electrons. How easily an atom loses an electron is called an ionization, to go from an atom to an ion. Metals would rather lose electrons because they have fewer electrons in their outermost energy level. When a nonmetal gains electrons, it becomes an ion. I always think of this as a negative ion. Nonmetals have high electron affinities. That's a vocab word from last term to describe how easily an atom gains an electron. The word affinity, think of it as attractive. How attractive an atom is pulling an electron towards itself. Remember, nonmetals have many electrons in their outermost energy level. They'd rather gain a few than lose many. Gaining an electron